In this Module 2 video, we'll be talking about adjusting measures. Our objectives are to define selection bias and talk about strategies to reduce it, define confounding and identify strategies to control it, and talk about how to calculate adjusted rates using direct and indirect standardization. So first, let's talk a little about types of error. There are two broad classes, random and systematic. Random error, also called statistical error, are unpredictable errors that happen from variation in measurement. So this could be because your measures are imprecise, so maybe you have a blood pressure cuff that isn't entirely accurate. You could have some kind of sampling error, so making mistakes in terms of defining your sample or collecting information from people within it, and variability within measures themselves. So using blood pressure, again, there's some natural variability in that, so there might just be some random error across people over time. Systematic error, on the other hand, is a type of predictable error that happens because we've poorly designed our study in some way, and so that results in bias. So basically, the primary difference between these two is that random error happens without regard to other variables or factors, whereas systematic error depends on some other kind of variable or factor within your study. So at the bottom right here, you can see visual representations of what happens when we have these two types of errors. On the far right is the ideal setting when we have small random error and small systematic error. So assuming that bullseye is the truth, our data points are all pretty closely clustered around it in that scenario. But if we have small statistical error and large systematic, the farthest left example, we still see pretty tight clustering, but it's pretty far off the mark, so we've made some kind of mistake in capturing the truth. The next figure, next bullseye, shows large random error and small systematic error, so those are just kind of data points all over the place. The third one is the case when we have both large random error and large systematic error, so broadly scattered but also off the mark. Just as a reminder, when we calculate a rate, we are talking about the number of events that happen in our population during a specified time period, and we divide the number of events by the number of people in our population who are at risk for the event during the same time period. So one of the times that this adjustment really comes up is when we're talking about rates and comparing rates across populations or over time. So accrued rate is just the observed number of events over the population size. So this is what we calculated in assignment 1 when we were calculating incidence rates. Those were accrued. It was just one number divided by the other. If we want to adjust those numbers, it's an approach in which we modify that accrued rate to account for some kind of underlying differences in the populations that we're comparing. So often we do age adjustment, and we'll talk about that today, but we can adjust for any number of things. We just want to have some clear reason for doing so. So here's an example of accrued rate versus an age-adjusted rate. This is the mortality rate in the US from 1960 to 2007. And you can see the accrued rates along the bottom. And if we were looking at that, we might say, there was a decrease in the mortality rate in the US over this time period, but it wasn't substantial. However, if we account for the fact that the population actually aged over that time period, so on average, Americans got older between 1960 and 2007, if we account for that fact, then we see a much more dramatic drop in mortality rate in the US, and that's just accounting for the change in the population age distribution over the time period. So another way that we can get systematic error is by having selection bias. And that is a situation in which we select people from the population that don't accurately reflect that population. So this can happen if we just invite volunteers to join our study, or if we only collect information on a sample of volunteers. Volunteers may be more healthy than people who don't volunteer to participate. So that could result in selection bias. It also can happen if we're offering some sort of payment or other incentive. People who most need that money or need the incentive might be more likely to participate than those who don't. Also, if we excuse me, are collecting our sample from within a healthcare setting, we want to keep in mind that the people who are receiving healthcare treatment or receiving more frequent treatment may be the ones who are more likely to show up in our sample, which may not be representative of the underlying population. And finally, we might recruit from one area in particular within a city or within a county, and that might not accurately reflect the full city or county population. So on that last point, here's an example of how poor geographic sampling could influence study results. So this is showing the rate of lower limb amputation among people with diabetes age 45 and older in LA County in 2009. And so the darker the color, the higher the rate of amputation in that area. So you can imagine if you were doing, if you were trying to understand the distribution of diabetes or risk factors for diabetes, or even diabetes related behaviors, medication adherence, for example, among people with diabetes, you can imagine that if you sampled primarily from the southern part of the county around Compton, you might get very different results than if you had drawn your sample primarily from the western part where you're focusing around Malibu. These are people who've already had amputations, and so their diabetes control is probably poorer. So if you were sampling in the kind of Compton region of the county, you'd probably get results that indicated poorer diabetes control than if you were sampling in the part of the county around Malibu. Likewise, this map shows income, so it's a proportion of households below the poverty limit. And we see the same sort of pattern. The same parts of the county that had high rates of lower limb amputations also have high rates of poverty, households in poverty. So again, there are these differences across the county. So depending on how you sampled, where you sampled from, you might get very different results. And this is just the results slide from that particular study, which did indeed show that there was this relationship between the percentage of households in poverty and the lower limb amputation rate among people with diabetes, in that as there were more and more households in poverty, the rate of amputations was also higher. Another type of bias is what we call information bias, and there are lots of ways that this can happen. I have two common examples here. One is recall bias, and so that happens when people who have a disease remember their past exposures differently than people who don't have it. And we'll talk more about study designs later, but in case control studies, when we sample people with and without a disease and ask them about their past exposures, we often worry about recall bias. If somebody has been diagnosed, they might have spent more time thinking about what might have caused their disease. So they might more accurately remember past exposures than someone who hasn't spent a lot of time thinking about things that might have caused their condition. Social desirability bias is another type of information bias. And this is when people give us answers that they think we want to hear. So if you're asking people about, fat intake or the physical activity, they might tell you, give you kind of an inaccurate response because they know they're supposed to be limiting their fat intake or doing more activity. So we can minimize this in several ways. One is by making sure that our questions are not leading, that we ask them in a neutral way, and that we give response options that cover a wide range of experiences. There's some evidence to suggest that people like to give responses that aren't on either end of the scale. So for example, if you're asking someone about how many drinks per day they have, assuming that they have more than 0, you wouldn't want to ask 1 drink, 2 drinks, or 3 drinks or more, for example. That's not a wide enough range, and people are more likely to say 2 even if they have more than 3. It would be better to give responses that are something like 1 to 2, 3 to 5, 6 to 8, so that people feel like they're not outside of the norm. Confounding is another type of bias. It could be labeled kind of as information bias, but it happens when there's an imbalance in some characteristics that's causally related to the variables that you're actually studying. So in this diagram, we want to know if the country that you live in is associated with the risk of death. So is the country associated with mortality rate? And so a big confounding factor that we'd be concerned about here is age, because the age distribution in different countries may be very different. And we know that as your age increases, your risk of death goes up. So a country may look better or worse than another country based purely on the fact that the age distribution is different, not on any differences in health status or healthcare quality or other things that we might actually be interested in. So here's an example of population pyramids. So the US is shown on the top left, Syria on the top right, and then Japan at the bottom. And population pyramids, if you're not familiar with them, just show the number of people in each age group by sex. So for example, if we look at the US here, the 0 to 4 is the youngest age group. We can see that there's about 9.5 million women aged 0 to 4 in the US in 2015, and about the same number, maybe more like 10 million males aged 0 to 4 in the US in 2015. So the structure, the shape of a population pyramid can give you a sense at a glance of how old a population is. So if we look at the US, we see that a lot of the population is concentrated in kind of the middle age years. Japan, it's even a little bit older. So middle-aged and older adults make up the largest proportion of the population. But if we look at Syria, we see that it's a very young population. So the vast majority of people are in those younger age groups. So if we were comparing mortality rates across the three countries, we would probably want to age adjust them because we can see that there are very different age distributions in each of their populations. Other potential confounders that we often think about are sex. This could be because of biologic reasons or social reasons. Race and ethnicity is another one, particularly in the US, that we look at. Again, this is largely a social construct, but it kind of is a reflection of other underlying characteristics like inequity in access to care or wealth. Socioeconomic status is another potential confounder that you'd want to consider adjusting for when you're comparing the health of populations. It's related to lots of different things, including occupation, income, and education. And it might be important to look at the time sequence. So did the health problem cause someone to become lower SES because they became unable to work, for example, or did low SES contribute to the development of their health problem? And social class is something that is important across countries. So it's been shown to be associated with lots of different health and health-related variables. So crude rates, as we said before, it's just as it occurs. And they don't account for differences in the underlying populations. They're essentially just a weighted average of whatever age-specific rates are occurring in that population. So if the distribution of age differs, then the weights do too. So one way we can get around this problem with crude rate comparisons is by using category-specific rates. So for example, age-specific rates. So we might compare the 0 to 4 mortality rates in the US to those in Syria and to those in Japan. And that would be a more fair comparison than comparing the overall population mortality rate because it's a narrow category, and so the similarities are greater. Another approach, rather than comparing lots of different age-specific rates, since there can be a lot of them, is to just age adjust our overall number. So again, looking at the US and Syria here, we've turned those population pyramids on their side. And this is just highlighting the fact that 0 to 14-year-olds in the US make up 20% of the population, while in Syria they're a third. So here is an example of age-specific death rates. This is older US data from 2006. And so we have those similar categories to what we saw in the population pyramid, and under 1 death rate, 1 to 4, and so on. And then we have the total rate at the bottom would be the overall crude mortality rate for the US. And these rates are calculated, as we talked about before, just the number of events over the people at risk, which in this case is that entire population. And here we multiply it by 100,000. That's often how we report mortality rate. So 700 deaths per 100,000 population in the under 1 group in the US. So if we wanted to adjust that number, one approach is to do direct adjustment. And this is where we take a standard population. Usually we use the US population from 2000, excuse me, as our standard population. And so we just apply those age-specific death rates that we had from the previous slide to that standard 2000 population to get an expected number of deaths. And then we can just add those up and calculate a new rate, which you can see kind of towards the middle of this slide here. And that would give us an age-adjusted rate, so that we're applying the 2006 rates to the 2000 population. So it gives us a sense of, if the population hadn't changed over time, what would this mortality rate translate to? So you can only do this if you have those category-specific rates. And as I said, the 2000 US population is kind of our go-to standard population, but it doesn't really matter. You can use any population you want. You should note that the number that you get, the adjusted rate that you get, will differ depending on the standard population you use, but the comparisons that you make, the inference that you make based on it, won't change. So here's another example of using direct adjustment to adjust rates. So we have these two communities here, and we're looking at the number of lower limb amputations per 1,000 population per year. And we see that in community A, we had 1 amputation. In the under 35 group, and there were 1,000 people. So that gives us an age-specific rate of 1 per 1,000. And there were 15 people aged 35 to 64 who had an amputation out of 3,000, and then 50 people out of 5,000 in the 65 and older group. So we just calculate those age-specific annual rates and do the same in community B. And then we want to age adjust it, because if we look at these two communities, we can see that the age distribution is different. So community A is older. A larger proportion of their population is 65 and older than in community B. So we already know that there might be some issues comparing these two groups' rates. So if we go on to this next slide, we can see that if we calculated the overall crude amputation rate in community A, we would just add up all those group level numbers. So we'd have 66 amputations out of 9,000 people, and that gives us an overall crude rate in community A of 7.3 amputations per 1,000. Do the same thing with community B, and we come up with a crude amputation rate of 7 per 1,000. So those look pretty similar. Based on the crude overall amputation rates, we'd say it's pretty similar in community A and community B. But the problem is, if we go back and look at those two age-specific columns, we see that in each case, community B has twice the rate of community A. So twice as many amputations in the under 35 group, twice the age-specific annual rate for 35 to 64, and twice as high among 65 and older. So anytime you see a discrepancy there where the crude overall rate looks the same, but age-specific or stratum-specific estimates look different, you know that there's probably some kind of confounding or some kind of issue going on there. So to address that, we'll age adjust all of these rates to get an age-adjusted overall rate. And that's what we're doing in the second two columns, or the last two columns of this table. So we have our standard US population. We just apply our age-specific rates for each community to that standard population to give us an expected number of amputations per year, and then add those up, and we come up with a much better comparison. So now we have an age-adjusted rate of amputations in community A of 3.7 per 1,000 people, and an age-adjusted rate in community B of 7.4 per 1,000 people. And now we see that that overall rate is indeed twice as high in community B as it is in community A, which matches our earlier observation that within each age stratum, the amputation rate was twice as high in community B as it was in community A. So the other approach, if you don't have those category specific estimates, age stratum specific estimates, you can use indirect adjustment or indirect standardization to account for differences in your population. And so in this approach, you actually use the stratum specific estimates from the standard population. So that's this middle column here in the slide. So we don't know the number of events, for example, among 15 to 24-year-olds here. We just know the population size. And so we apply the known death rates in our standard population to that population of interest, come up with an expected number of deaths, and then and that number is 987.9. And we do know that overall, across all these age groups, there were 502 deaths in this population. So then we calculate what's called the standardized mortality ratio, where we divide the observed by the expected number, and we get 50.8% in this case. So this is essentially saying that there were about half as many deaths as we would have expected in this population during this time period. So it's a lower mortality rate than we would have expected. We talked about direct and indirect methods of adjustment, and those are both great especially when you have just one variable you want to adjust for. But you can imagine if you wanted to age and sex and income and race ethnicity adjust these estimates, it would get messy. So we often use regression when we have multiple variables that we want to look at as adjusting for. And we're not going to go into the details of that for this class, but essentially you can put them in a regression model, linear or logistic regression, and account for all those different variables at one time. Just one final note about measurement and comparing measures across populations or time. You want to think about the timing if you are looking at something like an infectious disease, keeping in mind that there are periods when something might be endemic or kind of at the standard level, and then when you might have an outbreak or an epidemic, when your numbers of events or cases exceeds that expected level. So if you look at the slide here, this is kind of a standard. This one's for pneumonia and influenza, and this is common for other kinds of infectious diseases where we see a cyclical trend where in the winter months we see more cases. So if you were measuring at two different time points, if you wanted to make comparisons across years or across populations, it would be important to either make the measurements at the same time so that you are in the same point in these curves, or to account for the fact that you've made measurements at different times.